So for that, we have to look at the shape of the molecules. So I just quickly went through and said, well, basically it's based off this theory called VSEPR theory, valence shell electron pair repulsion theory, which basically says that all those electron pairs we use in the Lewis structures, some were bonding pairs, some were non-bonding or lone pairs. Well, all those pairs of electrons have a negative charge, so they therefore are going to repel each other and try to get as far apart as they can, right? And then I said, okay, well, there's basically 3 different scenarios we're going to look at with these groups of electrons. But first off, though, one more reminder, a group of electrons, a group of negative charge, can be a lone pair, a non-bonding pair, or it can be a bond, where that bond is single, double, or triple. It's still a group. So for example, then, a double bond is not 2 groups of electrons. It's still a group of 4 electrons. A triple bond is not 3 groups. It's still a group now of 6 electrons. So any kind of bond or a lone pair. And yesterday in lab I said this, people were still getting it wrong like crazy. So make that note. Any kind of bond, single, double, or triple, is still a group, or a lone pair is a group of negative charge. And those groups want to get as far apart as they possibly can. So there are 3 scenarios we're going to look at. We're going to look at the scenario with 2 electron groups, with 3 electron groups, and with 4 electron groups. And we can go up to 5 and 6, but not in this class. So yeah, come back in 110 and we'll do lots more groups. So we said last time, the best way to get 2 things as far apart as possible around a central atom is to put them basically then on opposite sides, right? So linear. So if you got 2 things, put them 180 from each other. We said if you have 3 things, we're going to put them basically on 3 corners of a triangle, which we call trigonoplanar. That's 120 degrees. And if we have 4 things, we said the best way 3-dimensionally is actually not 90 degrees, like you might expect. It's 109.5, which is called a tetrahedral geometry. Okay? So those are the 4 electron geometries we're going to look at today. So linear, trigonoplanar, or tetrahedral. Okay, well that's the way the electron groups are going to arrange themselves. But we said though, electron group, it might be a bond to an atom, but it also might be a lone pair that's not actually attached to anything. So the electron geometry is not the same as what we call the molecular geometry if you have lone pairs on that central atom. Because basically the molecular geometry, you are just looking at the atoms. The lone pairs, they are actually occupying space, but they're invisible because they are not attached to an atom. So if you have lone pairs in that central atom, the electron geometry is not the same as what's called the molecular geometry. So let me give you an example. Let's look at ammonia. So we know how to draw this Lewis structure now. You would write nitrogen with 3 bonds to a hydrogen and then a lone pair. So let's just think about here for a second. Okay, so how many electron groups are on that central atom? So again, we're only looking at the central atom, not the hydrogens, just the center atom. So we're focusing right here on the nitrogen. So how many groups of electrons are clustered around that nitrogen? What do you think? How many? 4, yes. This bond has 2 electrons, this bond has some electrons, this bond has some electrons, and then this lone pair has some electrons. So we have 4 electron groups. Do you see that? So, what's the best way to orient 4 things to make them as far apart as possible? Which geometry do we use? Tetrahedral, right? Tetrahedral. Right, that's the best geometry for that. It's tetrahedral, we said. So, you can imagine then a nice pyramid, and each corner of the pyramid has one of those groups of electrons. Now, 3 of those groups are bonded to a physical atom there, right? You have an atom. But one of them is just a region of negative charge, not actually attached to an atom, just a lone pair. So again, when you look at it, though, and you just consider the atoms, that doesn't look tetrahedral anymore. It doesn't look like something with 4 different objects around it. It only looks like something with 3 coming off of it. Can you see that? So it looks different when you don't consider this anymore. So then in this case, the electron geometry is not the same as the molecular geometry. Now, if there were no lone pairs, it would be the exact same. But there are. So if there's lone pairs, like I said, on the center atom, it's going to be a different molecular geometry. So in this case, we call this trigonal pyramidal. Trigonal pyramidal. Some people say it trigonal pyramidal, but I always learned it pyramidal. Okay, so let me go through the 6 possible cases here with you for the 6 possible molecular geometries. I'm going to build a little molecule here for you as we go, just to kind of illustrate here with you. So let me grab out a quick molecule here for us. Okay, so we're going to be referencing this table in your book, 5.16, but I am going to go ahead and actually draw this table too, just to kind of walk through it with you. But yeah, I'm just going to make a note. You need to memorize table 5.16. You need to learn the 6 geometries, and I'll show you it's not that bad. Seems big and scary, but once I break it down for you, it's not that bad. Okay. So like I said, I'm going to go ahead and just kind of recreate this table. And you can do the same on your paper there if you want. So let's go through here and talk about a few different things. We're going to look first. We want to know what's the number of electron groups. That's the first thing we're going to look at. Oh, it's kind of off the top of the screen there. Number of electron groups. I put E negative groups. Okay, then we want to know number of those that are bonding. And number of lone pairs or non-bonding. Supposed to say number of. Then we have the electron geometry. And then the molecular. Molecular may not fit on here. Nope, definitely not going to fit. It's supposed to say molecular geometry. But your paper is wider than my screen, so hope you can make molecular geometry fit on there. Okay, so that's what we're going to look at here. So I told you there's 3 cases we're going to look at, 2, 3, and 4. So let me look at, oh, you know what, because I used my big fat marker, I realized not my skinny pen. Oh well, too late. So let's look at 2 electron groups. Well, if you have 2 electron groups, there's only one case where they're both bonding and there are no lone pairs. So if they're both bonding and there's no lone pairs, well, we said the best way to orient 2 things is linear. 180 degrees, linear. So if I have a linear, let's build a linear one for you real quick here. Okay, so can you see? So here's linear, right? So here's the central atom. It's only got 2 things. The best way to get them as far apart is linear, 180, right? Well, if they're both atoms, then it looks linear too. So the molecular geometry is the same. Like I said, if there's no lone pairs on the center atom, then the molecular geometry is the same as the electron geometry. Okay, that's the first case. So I'm going to draw a little line. Let's look at the second case here. Well, the second case is if I have 3 electron groups. Well, there's 2 possibilities. Either they're all bonds, 3 bonds and no lone pairs, or 2 of them are bonds and 1 is a lone pair. There's 2 possible cases. Okay? So we said, what's the electron geometry called for 3 things? Do you remember? What is it? Trigonal what? Trigonal planar. It is a flat triangle. Yes, and that's the same for both cases. Because the electron geometry, we only consider those groups of electrons. So, here is a trigonal planar one. It's a flat triangle, right? See that? And they're all 120 apart. And they're all atoms. So, if they're all atoms, in the first case, they're all atoms, no lone pairs, well then it looks trigonal planar too, right? You see that? So, same molecular geometry. Trigonal planar. Trigonal planar. But what if one of these was not an atom? What if one of these was a lone pair? Now it does not look trigonal planar anymore, does it? You see that? What's it look like now? It's kind of bent. That's the name. Bent. We call that bent. So it just plain looks different when you don't have all the atoms there. Okay. The last scenario is going to be, what if we have 4 electron groups? Well, there's 3 options for this. All 4 can be atoms and no lone pairs. 3 can be atoms and there can be 1 lone pair. Or there can be 2 of those can be atoms and 2 can be lone pairs. 2 and 2. Which this screen will come down. 2 and 2. See if I can write it a little higher so you can see it. You can kind of see it. Okay, so what's the best way to arrange 4 things? Tetrahedral. Yes, thank you. Okay, so that's the same electron geometry for every case. Tetrahedral, tetrahedral, tetrahedral. So, here is a tetrahedral molecule. I don't know if you can see this, but there's 4 things attached, and no matter how you turn it, they're always 109.5 apart, right? They're all maximum apart, right? No matter how I turn it, they're all the same. Okay, and it looks tetrahedral, right? You can kind of see it looks like a little 4-sided pyramid in a sense, where we have 4 sides. Okay, so if they're all atoms, then again, the molecular geometry is the exact same as the electron geometry. It looks tetrahedral too. Okay, well how about the next case, where 3 of them are atoms, but 1 of them is a lone pair, so you no longer have an atom here. Now it does not look like a little pyramid anymore, right? It looks, right, or not like a little tetrahedron at least, right? See that? It looks differently. So this has a different name. That's what I just showed you for ammonia. It's called trigonal pyramidal. Trigonal pyramidal. Yeah. You know, you may hear, like I said, pronounced pyramidal. Okay, well that's the case where 3 are still atoms. So again, I mean, these 3 are still 109.5 apart. They don't suddenly change and become planar. They stay where they're at because there is another electrons here. You just can't see them. Well, what if 2 of these are atoms and 2 of these are lone pairs? Now what's it look like? Bent again. See that? Bent. bent. Sorry. Okay, so let's try a few of these examples. Try to make it make sense. Let's look here. So number 8 on your handout says basically we're going to do number 7 again. Because number 7 we drew the Lewis structure, which was the 2-dimensional version. Now we're going to take those ones you drew on number 7 and we're going to figure out, okay, so based off the Lewis structure, what's the 3-dimensional geometry of it? What's it actually look like? So I'm just going to draw them real quick and again, just kind of remind you because we already drew them last time. So let's look. So H2S, we drew it like this. Right? So that's what you ought to have in your notes. So how many? So we're just looking at the center atom, just the sulfur. How many electron groups are on that center atom? 4. Here's some electrons, here's some electrons, here's some electrons, here's some electrons. Awesome. So, what's the electron geometry called for 4 things? Tetrahedral. Good. Now, the molecular geometry is going to be the exact same if there aren't any lone pairs. If they're all atoms, it looks the exact same. But in this case, there are some lone pairs, right? So what's it called when 2 are atoms and 2 are lone pairs? Bent, yes. It looks just like this one, right? Like this, right? So 2 are atoms here, and then up on top there are 2 lone pairs you can't see. Good, okay. Let's try the next one. SiF4, so we drew it last time, and it looked like this. And then a whole bunch of lone pairs. Okay. Now, yes, we had all those lone pairs, but they don't really matter because they're not on the center atom. We're just focused on the center atom here. So how many electron groups are on the central atom? 4 again. Electrons, 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 electrons. You see that? There's 4 electron groups on the silicon. So all the ones out there on the fluorines, they don't matter for this. We're trying to figure out, on that silicon, how are they going to arrange themselves? Okay, so what's the molecular what's that what I just said? Electronegativity? What's the electron geometry for 4 things? Tetrahedral, yes, tetrahedral. What's the molecular geometry? They're all atoms, so yes. No lone pairs, so it's also tetrahedral. It looks tetrahedral too. Kind of makes sense? Okay, your turn. Try the next 3. Again, you already drew them last time, so just peek back at how you drew it and figure out, okay, how many electron groups? Talk it over with a neighbor, find somebody nearby or across from you, or move around if you need to. Yeah.
So a double bond is like just 1 bond.
A double bond is what?
Does a double bond count as?
It's still 1 group of electrons. Yes, right. Yeah. All right. Because a double bond, it's still 1 group. It's like 2 groups. 2 groups that can actually split apart. It still has to stay together. So, for example, in an oxygen-hydrogen bond, yes, there's oxygen sharing electrons with hydrogen. That's what a bond means. But the question is, are they sharing them right down the middle equally? Well, no, because oxygen is more electronegative than hydrogen. So these electrons actually shift this way towards the hydrogen. So they're spending more time over here and less time over here. So you can kind of see this little picture shows a bit of the likelihood or the probability of where to find an electron. And you're much more apt to find them over here, you see, than you are over here. Well, again, electrons have a negative charge, right? So if the negatives shift a little bit more towards the oxygen, well, that makes the oxygen side of the atom partially negative. So this end is partially negative, and the hydrogen end becomes partially positive. So that's the little lowercase Greek letter delta. It's a lowercase delta. It means partially or slightly. So the oxygen is partially negative. The hydrogen becomes partially positive. So yeah, they are sharing them. They're just not quite sharing them equally. Oxygen's pulling a little bit more on them than hydrogen is. So when this happens, and now I've created a negative side and a positive side, we call this a dipole moment. So you know how, like, on Earth we have a north pole and a south pole? That our planet has two poles. Same thing. Dipole, two poles. I've got a negative pole and a positive pole. I've got two poles, so it's called a dipole. So you often see these written with little vectors like this, where they draw a little arrow pointing towards the negative side. They put a line on the positive end like this. So this is what you'll often see dipole moments written. If you had any kind of vectors like in math, calculus, or physics, this should look kind of familiar to you. So we're basically looking at vectors, the way the electrons are shifting. So just draw a little arrow with a little, basically it's a little plus sign down here, right, on the positive end, pointing towards the way the electrons are moving. Okay, so that's a dipole. So if we have a covalent bond, again, sharing electrons, but they're not sharing them equally, we call it a polar bond, or a polar covalent bond, because we've made two poles, a positive pole and a negative pole. So it's a polar bond. They're not sharing them equally. Polar, polar, polar. Yeah. Towards the negative. Yeah, so you draw it like this, with the plus on the other end, kind of. So yeah, the plus is on the positive end, basically, see? Okay. So how do we know? Well, here's a value of here's the value of electronegativity values, and I would give you these values on a test or quiz. You need to memorize them. But this was created by a very famous American chemist named Linus Pauling. Anybody ever heard of Linus Pauling? He was a brilliant American chemist, won the Nobel Prize twice, not just once, twice, once in chemistry and once in peace, actually. This was one of his many contributions. So basically what he did was he just tried to create a scale of the most electronegative atoms and the least. And he just kind of chose 4.0 as the high. So 4.0 isn't actually a measurement of anything per se, it's kind of a number where 4 is the biggest. So it's kind of like a GPA, right? You know, 4.0 is the highest and then down from there. So you can see the most electronegative element is fluorine, right? So whenever fluorine gets into a tug of war with some other atom, fluorine always wins and winds up pulling the electrons towards it and away from the other one. Then you can see the next most electronegative is oxygen, right? And then nitrogen and chlorine are both tied, and then so on. But in general, the way it changes on your periodic table is it kind of increases going up and to the right, right? So it goes increases going up and increases going to the right. Yeah.
So because of an overlines hydrogen more electronegative boron?
Then which one?
Boron?
Then boron.
Is it boron or right? Yeah, so more.
Yes. Well, it depends where you draw hydrogen on your periodic table. Because on some periodic tables, it's written right above lithium, On some, it's written right above fluorine next to helium. Because hydrogen, remember, is really a non-metal. Remember, it's not, but it's kind of written above all the other metals, so it's not really there. It could kind of go multiple places. So yeah, you're right. It is kind of a goofy one. Hydrogen's kind of a goofy one. But notice, all of these noble gases down here, they have no value at all. They have no value at all for electronegativity. Why would the noble gases have no electronegativity at all?
Because they're the most stable.
Because they're the most stable. Why are they the most stable?
electrons.
Yeah, they already have 8 electrons, right? They don't want any more electrons, right? So there's no reason for helium then to try to go out and try to take someone else's electrons because it doesn't want any more. It's already got its stable noble gas configuration. So yeah, so those don't want electrons. So it ends up at fluorine. Yes, and hydrogen's kind of that weird one. You're right, because it's on the metal side sometimes, but it's really a non-metal, so it's kind of squeezed in there. So what you can do then, is you can say, okay, so let's say I have an oxygen-hydrogen bond. Well, if you find oxygen, its value is 3.5. Hydrogen is 2.1, right? So that's a difference of 1.4. So that was pre-lab question 3, right? So it said calculate the value for the polarity using these. So you just take one minus the other. So where's that threshold where it's different enough to be polar or not? So first off, let me show you what a non-polar one looks like, and then I'll come back to that. So I said if they're not sharing them equally, then it's said to be polar, because I've created a positive pole and a negative pole. If they are sharing them equally or nearly equally, so again, what's nearly mean? Well, now they're basically sharing them equally, and that's said non-polar. So polar and non-polar. So for example, let's say I have the case of 2 chlorines sharing electrons. Well, obviously, 2 chlorines are the exact same atom, right? So each chlorine is going to pull equally on the electrons. That makes sense? Because they're the exact same, right? So it won't shift one way or the other because each one has the exact same electronegativity strength. Okay, so what does nearly equally mean? So if the difference in the electronegativity values is from 0 to 0.4, that's considered nonpolar. So let's make a little note. From 0 to 0.4, that's nonpolar. From 0 to 0.4, that's nonpolar. So if the difference is 0 to 0, consider that nonpolar. Close enough, they're basically sharing them equally or darn close, that's nonpolar. If we are above 0.4, so we're like 0.5 up to about 2.0, now they're not sharing them equally. Now one atom is definitely pulling them a little more towards itself, and that's polar. That's a polar bond. And then if we get above 2.0, well, now they're not even really sharing at all. One of them is totally dominating and just backhanding the other one. It's like, give me that electron. Just taking those electrons away. So that's an ionic bond. Now we've actually transferred it from one to the other. So if the difference is 0 to 0.4, close enough, nonpolar. 0.5 to 2, still sharing, but not equally, so polar. And above 2.0, now there's no more pretense of sharing. One is just, like I said, backhanding. Like I said, just taking the electron, and now it's an ionic bond at that point. Okay. So, well, just because a bond in a molecule is polar doesn't necessarily mean the whole molecule is polar. Okay, just because the bonds are. Still, the best way to figure out, well, is the overall molecule polar or nonpolar, is based on symmetry. So, if everything is symmetrical around that center atom, in a sense then, if the electrons are symmetrical, so they're all moving equally in every direction or whatever, then it will be nonpolar. So this is going to be your friend today. Symmetrical versus asymmetrical. So if it's symmetrical around the center atom, it is a nonpolar molecule. Even if the bonds are polar, doesn't matter. If they are symmetrically spread out, it's still nonpolar molecule. So I'll give you an example. Let's say carbon dioxide. So carbon dioxide, oxygen is more electronegative than carbon. So you see we have so this oxygen is pulling the electrons towards itself this way, right? See that? And then this bond, this oxygen is pulling towards itself this way. So I definitely have two polar bonds. But one of them is pulling left, and one of them is pulling right, and they have the exact same strength because they're both oxygens, right? So oxygen is pulling right, oxygen's pulling left. So overall, they're kind of like canceling out. Can you see that? They're not really, there's no overall, it's not like this one's oxygen, that one's fluorine. They're pulling differently. No, they're both pulling. If you can think of this in a sense as a rope, this one's pulling this way, this one's pulling this way with the exact same strength. So overall, nothing happens because of that symmetry. So it's non-polar. Because symmetrical. Symmetrical, symmetrical, symmetrical. Yeah, this is our friend, symmetrical. Well, what if it's not symmetrical? Well, then it's going to be a polar molecule. Let me show you an example. Let's say we have water. So water. Let me change that. So if you figure out water, it is a tetrahedral electron geometry, but it looks bent like this. So oxygen is more electronegative than hydrogen. So yes, this bond is polar. This bond is polar. So the way that I like to think about this is oxygen had 4 electron groups, right? 2 hydrogens and 2 lone pairs, right? But are all 4 doing the same thing? The answer is no, because 2 of them are hydrogens, 2 of them are lone pairs. You see that? They are not all the same thing. So therefore it is asymmetrical. So if these 2 are going up, then overall you can imagine everything's kind of going up. So yes, it's asymmetrical, so it's definitely polar. But the easiest way to think about it is, are all the electron groups the same? Oh, they are? Then it's nonpolar. Are they different? Is it asymmetrical? Oh, then it's going to be polar. So are all the electron groups the same? Nonpolar. Are they not the same? Polar. That's the easiest way to break it down. Look at the electron groups. Yes? Pretty much, yes. Okay. So here's a few examples I kind of drew out here for you. So HCl, chlorine is more electronegative than hydrogen, so chlorine pulls the electrons in that bond towards itself. So overall, is that molecule polar or nonpolar? Polar, yes, right? Because it's all going one way. It's not like it's counteracted by something equally pulling the other way, right? To counteract it. So yes, it's definitely polar. NH3 over here, number 2. There's 3 hydrogens connected to an oxygen, and all those bonds are going up. Is it symmetrical in every direction? No, because everything's going up. There's nothing counteracting it going down, right? There's a big fat lone pair up here. All right, big fat lone pair. Yes, so everything's going up. So there's nothing going down counteracting it. 3. There's a carbon, and there's 4 chlorines. They're each pulling out in all 4 directions. Now that's symmetrical, right? Because they're all chlorines. They're all pulling with equal strength in equal directions. So yes, that's definitely nonpolar. How about boron with 3 fluorines pulling out in 3 different directions? Also canceling out, nonpolar. How about this one? It's kind of like number 3, where there's a chlorine pulling up, but then there's 3 hydrogens not doing anything. That's definitely not symmetrical, right? If they were all chlorines, it'd be nonpolar. If they were all hydrogens, it'd be symmetrical and nonpolar. If they're not all the same, 3 are hydrogens, 1's a chlorine, therefore it's polar. Okay, so let's try a few of these. I'll do the first one with you, and then you guys can try the next one. So, we got to do everything from the start. We got to build the whole case here, draw the Lewis structure and everything to figure this out. You cannot just look at it and say, oh, definitely, or not. So, NBR3. So let's walk through those 5 steps I told you to write down last time. Go through. So step 1 said, add up the total number of valence electrons. So let's do that. So we got 1 nitrogen, and I've got 3 bromines. How many valence electrons does each nitrogen give? So it's in group 5A, so it gives 5, right. So 5 electrons. How many does each bromine give? 7. So that's 21 more. So how many total valence electrons do I have to account for? 26. Okay, that's my total. Step 2, arrange the atoms. So which one goes in the center? How do you know nitrogen goes in the center? Because it's the one that only appears 1 time in the formula. So I'm going to put nitrogen in the center. Then we kind of arrange the other ones kind of around it, right?
Well, there are 2 single ones. How would you determine which one goes in the middle?
Give me an example.
Is there a possibility to have like a 1 nitrogen, 1
HCO3.
Carbon is usually in the middle.
HCO3. So there's a sub-rule for that I said if it's ever hydrogen, oxygen, and something else,
Oh, that's right.
there's something else in the center. Or if it's carbon, carbon's always in the center. So there are little kind of rules for that. There probably won't be a case I can think of like that, really. Okay, so the next step is connect them with a single bond. Bond, bond, bond. Every bond contains how many electrons? 2, so I just used how many? So I subtract 6 from my total. I have 20 electrons left. Okay. Next, it said put on the remaining electrons as lone pairs around those atoms. Do the outside ones first. So every bromine has how many right now? Has 2 electrons next to it in that bond. So it needs how many more? It needs 6. I'm going to go 2, 4, 6. Now it has 8. 2, 4, 6. Now it's got 8. 2, 4, 6. So I just used 6 and 6 and 6. How many did I just use? 18. So I have 2 left. Next rule said, if you still have any left, put them on the central atom. So I got 2 left, so I'm going to put those 2 on that center atom there. Yes. Okay. So now I subtract 2, and I used them all up. I got 0 left. Okay, now I can determine the polarity. So, how many electron groups are on that center atom? I heard 3 and 4. 4 electron groups, right? 3 are bonds, 1's a lone pair. Are all 4 electron groups the same thing? No. 3 are bonding to bromines, 1 is a lone pair. So it's not symmetrical, so what's the molecule? If it's not symmetrical, the molecule is polar.
So basically, if there's a lone pair, it's not going to.
Yes. So, But you wouldn't know there was a lone pair unless you drew it out, right? Because you can't tell that from NBR3. You can't tell that. That's why you have to draw it out to see, oh, I see there's a lone pair here, so it must be polar. Yes?
There is a lone pair, that makes it polar.
Yes. Yep. If there's a lone pair, it's going to be polar. Okay, your turn. Find a buddy. Try S2Cl+. Now, just one more time, quick reminder, what does the plus mean you do?
You subtract
You have to subtract an electron from the total, because a plus means we lost an electron. So add up the 2 sulfurs, add up the chlorine, and then subtract 1 for that positive charge. Right. Try that out. Okay, let me show you what I got. Oops. I think it was like that, right? If you did not get that, you made a mistake.
All right.
Okay, lots of blank looks. Let me work through that one. S2Cl+, 2 sulfurs. Each of those gives 6. That's 12. 1 chlorine. That gives 7. And then a positive charge means subtract 1. So 18 total, right? Is that what you got? Put chlorine in the center. Sulfurs and 1 bond, 1 bond. That used 4. Now I've got 14 left. Every sulfur needs 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. How many did that use? 12. Now I'm telling you, you got to go through the steps, because I always have students say, oh, chlorine, it needs 4 more. I'm going to give it 4 more. You can't just pull electrons out of your ass. We've only got 2 left. So you can only give it the 2 we got left, right? Okay. Then I check and I see, oh, but look, chlorine doesn't have an octet, does it? Chlorine is still short. So I'm going to take one of those non-bonding pairs. I'll just take those, make them go away, and I'll move them over and make a double bond. Oops. But technically, I could have done the other sulfur too, right? So I could really have what's called a resonance structure. Draw my little double-headed arrow here, and I could have done it on the other side, over here, instead. So either of those was okay, although technically you would draw them both on a test or a quiz or something, because both are happening. Okay, so I'm going to look here and see how many electron groups are on that center atom. How many electron groups? I heard 2, 3, and 4. Here's some electrons, here's some electrons, here's some electrons. So there's 3. Are all 3 the same? 2 are sulfurs, 1 is a lone pair. So definitely not the same. So the molecule is polar. Yes, bingo, polar. Okay. Okay, did you do NH4 plus yet? Okay, try NH4 plus then. Talk it over. See what you guys think. I got this. What you got? Okay, how many electron groups are on that nitrogen? 1, 2, 3, 4. Are they all the same? Yes. So what's the molecule? Nonpolar. Okay, good. Okay, last thing, then we'll wrap up this lecture and do our quick lab, because it's not very long. So, we're going to talk, we've been talking about bonds. Bonds are the attractions within molecules, holding the atoms together. So those are within, so we call those intra, intermolecular, but now we're going to discuss forces between different molecules, so we call those intermolecular. Just like international, right, between nations, or interstate, between states. Intermolecular, between molecules. So not within a molecule, between them. So there's three types of forces we're going to look at. Three types of intermolecular forces. We're going to look at what's called dipole-dipole, hydrogen bonds, and dispersion forces, sometimes called London forces. Okay, so let me go through each of these with you. So let me go through dipole-dipole, let's go through hydrogen bondings, let's go through dispersion and explain them. So, I just talked about dipoles, remember? I said if a molecule is polar, it has a dipole. One side's become a little negative, one side's become a little positive. So dipole-dipole forces, those happen between polar molecules, because polar molecules are the ones that have dipoles. So you see this little picture here, I've got a bunch of little fluorine-chlorine molecules. Maybe you can tell that they're polar. So there's a bunch of little negatives on the fluorines, see that? And there's a bunch of positives on the chlorines, right? So, well, again, it's not a pure ionic charge. It's just a little bit positive and a little bit negative. But what do positives and negatives do when they get around each other? They attract each other. So basically what happens, if you have a bunch of polar molecules, the negative end of one molecule is attracted to the positive end of another molecule, and you get this kind of an attraction. So that kind of an attraction is called a dipole-dipole force, or a dipole-dipole interaction. So that's what dipole-dipole is. It's the attraction between polar molecules, the positive end of one molecule and the negative end of another polar molecule. That's simple as I can make it. That's what dipole-dipoles is. So only polar molecules can have this. Obviously, non-polar can't do this because they don't have dipoles, right? Okay. So, let me look here at a little chart and kind of show you the effect this has. So, the middle column is measuring that dipole moment. How strong is that dipole? And that's measured in a unit called dBs, that capital D, you don't need to worry about. But basically, you see for propane, it's 0.1. So it's basically nonpolar. It has no real dipole moment. And then as you go down, you see how they're getting more and more polar as we go down? Right? See that? They're getting more and more polar, right? Well, also as we go down, you see the boiling point is getting higher and higher. So as the molecules are getting more polar, they're also taking more energy to boil. You see that? So let's think about why would that be? Well, let's imagine I have a beaker here. Let's draw a little beaker. And in my beaker, I have some water. So I'll draw a bunch of little water molecules here. Or just anything that's polar, I guess, really, I could say. Okay, well, when something wants to boil, what has to happen? Well, I have to basically take those liquids to have an attraction. I have to break them apart to go into the gas phase, right? Well, the thing that's holding them together are these intermolecular forces. So if this molecule is polar, well, then the thing holding them together are dipole forces. So these are all being attracted to their neighboring molecules. So they all have attractions one to another. So in order for me to liberate one of these molecules and send it out here into space, when it boils, I have to break it apart and make it free, right? Oh, well, you can see as the polarity gets higher, it takes more energy to do that, right? Well, why? Because, again, it takes more energy to break it apart because they have a stronger force holding them together. So the bottom one there, acetonitrile, is the strongest, right? It has the highest polarity. It has the strongest dipole force. So it's really trying to cling together, so it takes the most energy to break that force apart and make it boil. Does that make sense? So you can see that, right? So as it gets more polar, stronger dipole, so it takes more energy for me to break these apart so they can fly apart into the gas phase. Okay. The next type of force is called hydrogen bonding. It is basically just a special type of an extra strong dipole-dipole. So, hydrogen bonding occurs in molecules that are still polar. They still have dipole-dipole, but they have a couple little special things going for them. They have a lone pair on the molecule, and they have a hydrogen bonded to either a fluorine, a hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen. So you have to have an HF, HO, or an HN bond, and you got to have that lone pair. Still, these are still polar molecules, but just the polarity is just extra special strong here. So let me explain why this is so much stronger than just a normal polar molecule. Why does it matter that it's hydrogen? Why does it lone pairs? So, got that written down? Huh? Okay, so let me show you what I'm talking about here. So let's say I have hydrogen bonded to one of these elements, oxygen, fluorine, or nitrogen. Well, it said those three are the most electronegative elements. So that means they want to take electrons away from hydrogen more than any other element. Well, normally, hydrogen has how many protons and how many electrons? Hydrogen's number one. So normally it has one proton, and then orbiting around it, it's got one electron, right? Well, when it makes a bond with, let's say, fluorine, well, now it's sharing that one electron with fluorine, right? So let's say here's fluorine over here. Fluorine's bigger, so it's got one S2, two S2, two P5. So here's my hydrogen, here's my fluorine. So fluorine is also sharing an electron, right, with the hydrogen. It makes my little hydrogen-fluorine bond. I got my hydrogen-fluorine bond here. But fluorine, we said, is the most electronegative element. So that means fluorine is taking these shared electrons and it is pulling them away from the hydrogen towards itself, right? No? Maybe? Yes, right? So hydrogen is fluorine is the most electronegative. So it's not sharing equally. It's grabbing those electrons and it's saying, give me those electrons, and it's pulling them towards itself. So that means, in a sense, when we're all done here, it's like, oh, here's hydrogen, here's fluorine, and the electrons are way over here by the fluorine. They're not shared in the middle anymore, right? So what does that leave hydrogen with? All it's got left is that proton in the center, right? So all I've got left over here is a big, juicy proton. So, it's not even just like, I mean, it is still a little bit positive, but it's really positive now, right? So it's, so like I said, they're polar, oh, it's a little bit positive, a little bit, this one is really positive, because basically all it's got left is a pure positive charge out there. Just a big, fat, juicy proton. A big positive charge out there. No, fluorine is the most electronegative element. Is that little chart I showed you? So fluorine's value is 4.0. It is the most electronegative element. Okay, so that basically means this is super, super positive, and now this side has become super, super negative. So So not quite a full-on 1 plus, but darn close. Well, now, let's say I have a whole bunch of these HFs lying around. So let's say I have HF. I'm going to draw a bunch of HFs here. So we know the hydrogen end is really, really positive, right? Because fluorine has basically taken its electron and left it with only a proton. So I can imagine there being an attraction between, because the lone pairs are what? What's the charge on the lone pairs? Electron. What are they? They're 2 electrons. So what's the charge?
Negative.
Negatives, right? Not a trick question here. Electrons are negative. So fluorine's got a bunch of big, juicy negative charges out here. So I can make a super great attraction between the positive on the hydrogen and the negative on those lone pairs. I could do this all day long, right? So that makes an even stronger type of force, because now I've got the really positive hydrogen and the really negative lone pairs. So it is still like the dipole-dipole, but it's just an extra strong version of that. So I've got really positive hydrogens drawn to really negative lone pairs, which are just pure electrons, pure negative charges. So that's hydrogen bonding. So remember though, but to have that, you got to have a lone pair, and you've got to have either that HF, HO, or HN bond, right? Okay? You got to have a lone pair, and you got to have an HO, an HF, or an HN bond. Okay, well, hydrogen bonds are super important, like in biology especially. They are all over your body. So, for example, you probably all know that DNA has this what's called a double helix structure, where it's 2 big strands of nucleotides, but they are wound around each other in a helix. Well, those 2 strands are not bonded together. The reason those 2 strands stay together is because of hydrogen bonds. It's actually this kind of an attraction that's holding them together. Because you'll see on one strand, it'll have lone pairs. And on one strand, it'll have a hydrogen bonded to an oxygen, nitrogen, or fluorine. So you have this really positive on one side, really negative on the other side, and that's what's holding them together. It's not actually sharing electrons in a true covalent bond. It's just this strong partial positive from all the way down the line. This also happens a lot like in proteins. So if you ever had a biology class, I'm sure you discussed structures of proteins and how proteins have what's called the primary structure. They get more and more complex as they begin to fold on themselves. You get like ternary structures and quaternary structures. Well, the reason proteins fold and make all these interesting shapes is, again, it's hydrogen bonding. They're trying to fold around, and those hydrogens are trying to find lone pairs to make attractions. So they fold around. So it happens in enzymes and proteins and all over your body. Super important. Okay. Well, the last type we're going to talk about are what are called dispersion forces. Sometimes an old school name is London forces. Not, by the way, named for the city. Named for something else called London. So these are very weak forces. But these can happen between any kind of molecule, any kind of atom even. So now it's not just polar ones. Or everybody has dispersion. Polar, nonpolar, atoms, molecules, everybody has dispersion forces. So what are dispersion forces? Everybody has dispersion forces. So let me explain what they are. Let me use helium as an example. I like this example. Let me use helium. So helium, find helium on your periodic table. How many electrons, how many protons? 2, right? It's number 2. So let's say I have a helium atom right here. It's got 2 protons, and then it's got 2 electrons, and the electrons are just doing what? What are they doing? They're just orbiting, right? They're just going wee, 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 or they're just orbiting around that nucleus, right? They're doing this, right? There's 2 of them doing that. Well, at some moment in time, as they're just going around doing their thing, you could imagine, just for a split second, maybe they both wind up on the same side. Okay? Just for a second, right? They're going around like crazy. They're just going around, and they happen to come into alignment on the same side. Well, in that split second in time, what's happened? Well, in that split second in time, this side of the atom has become partially negative. And this side, well, now on this side, all the protons are kind of exposed, and now it's partially positive on this side. But again, it's just there and it's gone again. It's just there for a second, and then they keep rotating, orbiting, and it's gone again. But in that split second, I have created what's called an instantaneous dipole, because in that instant, there is a dipole. It's called an instantaneous dipole. So in that instant, instantaneously there's a dipole and it's gone again. Because it just happens, for a nanosecond, so just there and gone. But let's imagine though, in that very little short time frame, there's another helium right next to it, hanging out here, and it's got a couple of protons, and it's got a couple of electrons orbiting around it. So what are the electrons on this helium going to do once they see the electrons on the first helium? So there's electrons here. Here's electrons here. So what will these electrons do to those electrons? Repulsion, right? We're going to make them repel. So electrons on the second one are going to go screaming, going to go, "Aye!" and they're going to run away as far away as they can from the first electrons, right? So now I have caused a dipole on the next one, right? The first one caused that one. So we call that an induced dipole. So I induced a dipole, just, like you induce labor. I caused a dipole to happen. So the first one, in that split second, had a dipole, and it caused another dipole in the one next to it. And that can happen down the line. But again, then it's just gone again just as fast, right? Because again, they keep moving and then it's all over. So that's why it's super weak, because it's not like a polar molecule where it's always partially positive and always partially negative. Just once in a blue moon that happens. So once in a blue moon you get a little bit of an attraction. So it's a super weak force compared to dipole-dipole or hydrogen bonding. Does that make sense? Because again, it's not all the time. Just once in a while that happens and it's gone. Okay, so again, but any atom can have that. Any molecule, polar, that doesn't matter. Everybody can do that because everybody has electrons orbiting around themselves. Now, this force, though, tends to get stronger as you get more and more electrons. Now, this is a big paragraph. You need to write the whole paragraph down. Don't write it all down. You'll be here all day. But basically, what's going to happen is here's the big takeaway point. Dispersion forces tend to increase as molar mass increases. Dispersion forces tend to get stronger as molar mass increases. The reason that is we just have, as they're getting heavier, we just have more electrons present. And as they're getting bigger and bigger, the electrons we'll see are actually getting farther and farther away from the nucleus, right? Remember that? So if they're farther and farther away from the nucleus, now they're not being held as tightly. So we can actually then begin to kind of smush them all to one side if we want to. So they're more spread out. They're not being held as tightly, so we can kind of smush them all more to one side. But again, you can, like I said, in 110, and I will tell you much more about that. But just generally, as they get bigger and they have more electrons, they're going to have a larger dispersion force, stronger dispersion forces. So heavier atoms tend to have stronger dispersion forces just because they have more electrons, more spread out, farther away, and they're easy to kind of morph to one side to make that one side partially negative and the other side partially positive. But if they're really close and held in tight, it's a little harder actually for me to kind of smush them one way or the other because they're being held so tight. Okay, so let me show you an example of this. here is 5 noble gases. Again, totally not polar. They're not even molecules. So they're not molecules, so they definitely don't have dipole-dipole. They definitely don't have hydrogen bonding. The only thing they can have is what I just showed you, which are the dispersion forces. So the electrons orbiting around there, at one moment in time, might kind of wind up on one side. Well, as they get heavier, and as they have more electrons, so here we have 2 electrons, 10 electrons, 18 electrons, 32 electrons, etc., getting heavier and heavier, have more electrons. Well, we can actually, like I said, as they get heavier, we can actually begin to imagine them all wind up on one side or another in that sense. Well, let's look again at our friend boiling point one more time. A higher boiling point tells me it takes more energy for me then to actually break apart the forces holding them as a liquid to make them into a gas, right? So you see, well, this has the highest boiling point down here, xenon. So it must have the strongest forces, right? And then they get weaker and weaker. So you see, yes, as the molar mass increases, the dispersion forces must be increasing as well because the boiling point increases. Does that make sense? Okay, well, let's try a lovely example here. So first I want to give you a little reminder, or not reminder, but it's in general, which of those kind of forces are the strongest? Hydrogen bonding are the strongest. What's next? Dipole-dipole, and then the weakest forces tend to be dispersion forces, London forces, yes. So, now, so if you're comparing a series of molecules, and they all have about the same molar mass, about the same size, then yes, hydrogen bonding wins, then dipole-dipole, then dispersion. But again, that's only if their masses are about equal. So now, let's say one thing had a mass of 10,000 and one had a mass of 10. Well, now you can't compare them because one of the 10,000 may have a really, really strong dispersion force. That makes sense because it goes so big, remember we said. So, but if they're all about the same mass, then generally hydrogen bonding stronger than dipole-dipole, stronger than dispersion. Good question?
That was what I was going to ask.
Yeah.
Does the element 118 have is it different in any way in terms of dispersion system?
Yeah. It's all basically, yeah. So yeah, if they're roughly the same mass, then you can kind of compare them side by side. So, as a quick reminder, which kind of molecules and atoms can have dispersion forces? Everybody. Everybody's got dispersion forces. Everything. Which kind of molecules or atoms can have dipole-dipole? Only polar molecules have dipole-dipole. And which kind have hydrogen bonding? Only polar molecules that have an HF, an HO, or an HN bond, and a lone pair, which I should add on to that. So, yeah.
And just to clarify for hydrogen bonding, it can have multiple HOs like H2O. It can have multiple.
Oh, yeah, sure. Yeah, definitely. You can have multiple hydrogen bonds. Okay, so let's look at 3 molecules. Let's kind of figure out what's going on here. So, they all have about the same mass. See, their mass is all, it's roughly 30. Right, see, 32, 30, 30. So they're all pretty close in mass. So the mass is not the difference. Something structurally is making methanol have a much higher boiling point than formaldehyde, which has a much higher boiling point than ethane. So let's look at the molecular structure here that we drew. So let's look first at ethane. So if I'm looking at ethane, what is that, a polar molecule or a non-polar molecule first off? It is definitely very symmetrical, right? So it is non-polar. Use a smaller pen. Non-polar. So if it's non-polar, what kind of forces can it have? All it can have is dispersion, right? Right? If it's non-polar, that's all it can have is dispersion. Okay, how about the next molecule? Formaldehyde. Used to embalm corpses. Isn't that nice? Formaldehyde. Is that polar or non-polar? That one's polar now, right? Because it's not symmetrical, right? You see that? It's polar. So if it's polar, yes, it has dispersion because everything has dispersion. But it also has what? Not hydrogen bonding. Why? It's polar, so we know it has dipole-dipole. And then I was about to ask, okay, does it have hydrogen bonding?
No.
Why not? I see hydrogens and oxygens. Why not?
They're not bonded.
Because the hydrogen's not bonded to the oxygen. I have to have a hydrogen-oxygen bond. It's not enough just to have a hydrogen-oxygen. They have to be bonded to each other. So, now how about methanol? Is that polar or non-polar? Is that symmetrical? Is that the same thing? No. One side hydrogen, one side. Yes, so it's definitely polar. So yes, so it has dispersion just because everything has dispersion. It's polar, so it has dipole-dipole. All right? And notice it's got a hydrogen-oxygen bond. So that means it also has our friend hydrogen bonding. So, now you can kind of see why methanol has the highest boiling point. Why does methanol then require the most energy to actually break apart the liquids? Because it has the strongest forces holding it together, right? And then the last one, ethane, is the easiest to break apart because it has the weakest forces holding it together. Yes?
Yes.
Okay. Last slide. Who's excited? Me? Okay. Okay. So your turn. I gave you 3 molecules. I want you to figure out one of these is a liquid. 2 of these are gases. So talk it over, reason it out, figure out which of those 3 is going to be the liquid and which is going to be, and which 2 are going to be gases. So first think about, okay, so liquid or gas, which one has the stronger forces now? So think about that, talk it over. Okay, talk it over with your neighbor. Find somebody. What do you guys think? Which one's the liquid? Which 2 are the gases? And then figure out why. Talk it over with somebody if you haven't yet. Okay, well, let's talk about it. So what do you think? Which molecule is the liquid? Hydrogen peroxide. Anybody else? Okay, so let me think about this for a second. So if it's a liquid, what's that mean compared to a gas? The one that's the liquid must have stronger forces still, because the ones that are gases have already flown apart. So whichever one has the strongest forces would be the liquid. So all of them have dispersion forces, right? Everybody's got dispersion forces. Okay. They are all polar too. So the first 2 are definitely polar, so they have dipole-dipole. but they do not have hydrogen bonding, right? So now I do see, oh, there's a chlorine and a hydrogen. Chlorine, what's that thing called? Oxygen and a hydrogen, but they're not bonded, right? Oh, here's a fluorine and a hydrogen, but they're not bonded, right? Aha, but here I have a hydrogen bonded to an oxygen, and here I have another hydrogen bonded to an oxygen. So they all have dipole-dipole, but the last one has the strongest force, right? The last one has hydrogen bonding. So yes, so therefore you would pick, yes,
Do you say that hydrogen process is polar?
it is polar.
How?
Because it really looks like, if you were to draw the Lewis structure, there's a whole bunch of lone pairs that aren't being shown there. So, it's a whole bunch of lone pairs. Because each of these is, this is tetrahedral, and this is tetrahedral. Let's not show them in this structure. Yeah, that's a good question, because you can't really tell that, because in the picture it doesn't look symmetrical. Good question. So hydrogen bonding is the strongest forces, therefore it's going to be the liquid one. Okay, yeah.
And fluoromethane is polar because it has the layers that have that line.
It's polar, but it's not symmetrical.
Okay.
Hydrogen, 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 fluorine, that's not all the same. If all four were the hydrogens, it'd be non-polar. For all four were fluorines, it'd be symmetrical. But they're not all the same. Okay, well, that is it.